All right, let's dive right into what is arguably the most mind-bending cosmic whodunit in all of physics. Welcome to this explainer. Today, we're unpacking a phenomenon so profoundly strange, so incredibly counterintuitive, it literally keeps physicists awake at night. We're talking, of course, about the infamous double-slit experiment. It's the ultimate test of wave-particle duality, and as we're going to see, it proves that the very building blocks of our reality absolutely do not behave the way you'd think.
Now, the legendary physicist Richard Feynman actually set the stakes for this perfectly. He called this single experiment the absolute heart of quantum mechanics. In fact, he went so far as to say it contains the only mystery. And honestly, he wasn't exaggerating. If you can wrap your head around what goes down in this one specific setup, you're essentially staring at the foundational puzzle of the entire quantum realm. It totally defies classical logic, and it forces us to completely rethink what it means for something to be, well, real. So let's head over to the physical crime scene and take a look at the setup.
Chapter 1. The Setup.
The physical parameters of this experiment are actually incredibly simple. We're basically looking at three things: a source gun, a barrier with two little gaps cut into it, and a photosensitive screen at the back. That's the whole shebang. All we're doing is firing something from the emitter. Could be a beam of light, could be tiny bits of matter, straight at that barrier. Whatever squeezes through those two parallel slits then smacks into the back screen and leaves a mark. It's kind of like a high-tech version of firing paintballs at a picket fence just to see where they splatter on the wall behind it.
And what's genuinely wild here is just how long scientists have been obsessing over this exact setup. Thomas Young kicked things off way back in 1801 using just plain old visible light, basically to prove light was a wave. Then, a century later, Einstein crashes the party and says, actually, light can act like a particle too. By 1927, Davison and Germer proved that electrons, actual solid matter, could do this. And get this. In 2019, scientists pulled off this exact same experiment using massive, complex molecules made of literally 2,000 atoms. So the scale scales up, but the core setup never changes. But to really solve this mystery, we first need to get a handle on how our two main suspects normally behave.
Chapter 2. The Suspects. Waves versus Particles.
Okay, so this brilliantly illustrates what we expect to happen. Imagine you're just dumping ordinary sand through two slots. What do you get? You get two neat little piles directly underneath the slots, right? That is classic particle behavior, right there. But what if you push water waves through those exact same slits? The ripples fan out, they overlap, and they create this beautiful, complex pattern all the way across the back wall. Completely different outcome.
So the absolute crucial thing to remember about wave behavior is how those ripples interact. When they overlap, they actually cancel each other out in some spots and amplify each other in others. This leaves a distinct, striped, almost barcode-like pattern on the back screen. Basically, when the crest of one wave meets the crest of another, they team up. They make a bigger wave, which gives us a bright band. But if a crest meets a trough, they totally destroy each other, leaving a dark band. We call this an interference pattern, and it is the absolute, unquestionable fingerprint of a wave. All right, now let's crank things up and shrink things down.
Chapter 3. The Quantum Twist. So we swap our flashlight for an atom gun. When we block off one of the slits and just fire atoms, they hit the back screen as these tiny localized little flashes. This proves, without a doubt, they're acting like solid individual particles. Since we're using a photosensitive screen, every single time an atom hits, pop, we see a tiny pinprick of light. The atom isn't washing over the screen like a water wave, it's landing at a super specific, localized point. So far, so normal, right? We fired tiny particles, they land as tiny particles.
But here is the million-dollar question. What happens when we open up that second slit? Think about it for a second. We just established they act like little grains of sand, hitting the screen at highly specific points. So common sense absolutely dictates that with two slits open, they should just form two distinct bands directly behind the slits. I mean, what else could they do? Well, let's look at the evidence.
Boom! First massive twist. We do not get two bands. Instead, these tiny individual particles somehow collectively build up the exact same wave interference pattern we saw with light. We get multiple alternating stripes of light and dark. It is absolutely wild. It's as if these solid little atoms travel through the slits, acting exactly like overlapping water waves. But how is that even possible? Well, a totally logical person might say, hey, you're firing a whole stream of atoms at once. Maybe they're just bumping into each other midair, bouncing around and coordinating their paths to form this weird pattern.
Okay, fair point. So to completely rule out these atoms secretly bumping into each other or, coordinating their flight paths, we run the whole experiment again. But this time, we fire them incredibly slowly. Totally alone, one by one.
We leave such a big gap that atom number 1 hits the screen way before atom number 2 even leaves the gun. There is literally zero chance for them to interact, communicate, or bounce off each other. They are entirely isolated. And yet, gradually, as the hours tick by, those completely isolated, totally solitary atoms still magically build up the exact same striped wave pattern. The physicist Jim Al-Khalili sums it up perfectly here. Every single atom, traveling utterly alone, somehow knows exactly where to land to contribute to this larger wave pattern. They show up as tiny distinct dots, but as those dots pile up over time, the interference fringes emerge loud and clear. This is the exact moment physics just shatters our everyday intuition. We have to ask, how on earth can a single, tiny, localized point possibly know that there are two slits available? Remember, to get an interference pattern, you need two overlapping waves. But we only fired one atom. For this pattern to show up, that single solitary particle must somehow be traveling through both slits at the exact same time, acting like a wave, interfering with itself on the other side, and then just deciding to become a localized particle again the millisecond it hits the screen. It's maddening. So, frustrated by this impossible result, we decide it's time for a quantum sting operation.
Chapter 4. The Spooky Observer Effect.
We decide to spy on the atom. What if we place a tiny, highly sensitive detector right above the top slit, designed to beep 50% of the time to catch the atom red-handed as it chooses a path? We just want a straight answer. Does it split in half? Does it go top? Does it go bottom? So we set up the detector, we fire the atoms one by one, and sure enough, beep. Our detector goes off half the time. We finally know the exact path these particles are taking.
But wait, as soon as we measure which slit it goes through, the wave pattern on the back screen completely vanishes. Poof, gone. The atoms immediately go back to acting like two simple piles of sand. I mean, really let that sink in for a second. Simply by placing a detector there to gather information, the physical outcome of the experiment completely alters. The atoms stop acting like waves, they revert to boring classical particles, and they just leave two distinct bands.
Honestly, it borders on the comical. If you leave the physical detector right there, but you secretly unplug it so no actual witch path data is recorded, those sneaky atoms instantly revert right back to their wave behavior. When the detector is actively recording, the universe behaves one way, like particles. Unplug it, and the universe behaves a totally different way, like waves. It's literally as if these atoms are aware they're being watched and they change their behavior just to mess with us. Now, Niels Bohr tried to explain this using what's called the principle of complementarity. He showed that the very act of extracting information from the universe fundamentally dictates how that universe behaves. You can set up an experiment to reveal the wave nature of matter, or you can set it up to reveal the particle nature of matter, but you absolutely cannot do both at the same time. The measurement itself literally collapses the wave-like possibilities down into a single concrete reality. So, how do the smartest people on the planet rationalize a verdict where just looking at reality actively changes it?
Chapter 5. Interpreting the impossible.
Well, physicists have come up with several wild frameworks to explain this, from splitting parallel universes to collapsing probabilities. But honestly, all of them point to a universe far stranger than we ever imagined. You've got the Copenhagen interpretation, which suggests reality is just this hazy blur of probabilities until the exact moment we measure it. Then there's the many worlds theory. This one argues that every time a particle hits those slits, the universe literally splits. It goes through one slit in our universe and the other slit in a completely parallel reality. Or how about the de Broglie-Bohm theory, which says there's a hidden pilot wave secretly guiding a real physical particle? And the relational interpretation? It flat out argues that an object literally doesn't even have absolute properties until it interacts with an observer. All of these are just desperate attempts to make sense of the exact same experimental evidence we just walked through.
Which leaves us with this incredibly profound, kind of unsettling thought. Is the world around you actually there when you turn your back? The double-slit experiment proves that at the most fundamental quantum level, observation is not a passive event. We aren't just sitting in the audience watching the universe play out. Our very act of observing actually shapes its reality. It's a mystery that remains at the absolute beating heart of modern physics. Thank you so much for joining me for this explainer, and definitely keep questioning what you think you know about the universe.